Good morning, Cisco Cohort 2. On today's schedule, we're going to be covering module chapters 8, 9, and 10, talking about network layer stuff, and a little bit about basic router configuration of the iOS, which is going to be very easy because it's exactly the same syntax as what we already learned on the switch. So let me share this. We're going to look at how the network layer uses, well, one of our protocols at layer 3 is IP protocol, IP version 4, IP version 6. We'll look at how those are set up, and we'll look at how a network device like a router uses routing tables to find a destination network. And there's also even a kind of a little routing table in your desktop machine because you need to know how to find this default gateway. So on the network layer, we have this dreaded, feared, and hated OSI 7 layer reference model, layer 3. So the properties we find there, the protocols we have running there is Internet Protocol version 4, IP version 4, IP version 6, IP version 4 is our legacy 32-bit addressing system, and IP version 6 is the one that came out around the turn of the century that has 128 bits. So it solved the problem with IP version 4 was simply running out of available addresses. So at the network layer, he's talking about the 4 operations that take place. We need to give end devices a unique address. This is the same exact concept as in the cellular phone system. Every phone needs a unique telephone number, mainly so they can send you the right bill. We're going to look at encapsulation and de-encapsulation. This operation of receiving some data on one port of the router, unencapsulating it, and then looking at the network information, and then looking at the routing table and determine where he wants to route that. At the IP layer, at the network layer is going to take the upper layer data, and the layer that's right above the network layer is the transport layer, and that's going to have a TCP or UDP, typically in the IP world, a TCP or a UDP encapsulated segment. The segment header contains such information. That's what's the port numbers, and the data is the actual fragment of the upper layer application data. Then that will be accepted by the network layer, and he'll create his own, he'll make his own protocol data unit called a network packet, and he's going to take that transport layer protocol data unit, the segment, he's going to place it in the data portion of the IP packet, and then he'll add the addressing information to the beginning of that, like what's the source IP address, what's the destination IP address. Notice this point here. Let me turn on my pencil. This is a very important point here. NAT will be in a later module. Let's forget about NAT for now, pretend it doesn't exist. Normally, when a packet is sent from source to destination through the average of 10 or 15 routers that it takes, the IP addressing doesn't change. Kind of think of it when a letter goes in the mail, they don't scratch codes on the envelope and scratch them out and put new codes on the envelope for each little trip segment that it makes from the plane to the truck to the mailman's in the letter bag to that white bucket in the post office where they sort mail and so forth. So the IP addressing of the layer 3 information stays constant. The layer 2 information, the data link layer information we talked about last time, yeah, that changes from link to link. You get a new set of MAC addresses as you go from one physical segment to another physical segment, but the layer 3 addresses will not change. So IP was connectionless. That means it doesn't have any its own built-in positive acknowledgement and retransmission. We put that up at the transport layer. We'll use TCP for that. It's best effort only. Now, best effort is a term that's the internet service from your cable company, your telephone company. It's not commercial guaranteed 5 nines reliability. It's best effort only. If it goes out, if you call a company, they might give you 1 day credit on your bill or something. And it's media independent, which means it can go over fiber optic cable, twisted pair cable, radio frequency energy, radio waves through the air. When I send a letter in the mail, what connectionless means is, let's say I send a letter in the mail to you, and it's just a regular letter. It's not like a return receipt request or anything like that. So I put a letter in the mail, and you'll never know the letter is coming until it shows up in your mailbox. So the letter goes from hop to hop to hop. The mailmen look at the zip code, and they sort the mail into the proper trucks, and eventually the letter shows up at the other end. There's no type of control information. You won't know when it's coming ahead of time. if this isn't, if you need more reliability than this, well, you can go to the post office and pay for, return receipt requested. They give you tracking number. You can track the mail as it goes through the system, and you'll get the sender will get a notification back. He knows that the receiver received that mail. But normally, mail is not like that. So best effort only. IP has, we have this diagram here showing 4 different routers. There's several different possible paths that these packets could take from one host machine on the left to the PC on the right. So packets get routed very quickly. No acknowledgments are sent back. There's no guarantees of delivery. And IP itself will never know if the other device received the packet. Now, at the next layer up, at the transport layer, yes, TCP knows. TCP very carefully tracks with sequence and acknowledgement numbers that each little bit and piece of the parcel of the data has been sent properly, and he can retransmit anything that was lost for any reason. That's his job, it's positive acknowledgement and retransmission. But there's nothing like that at the IP layer itself. So media independent IP, well, he says it's unreliable. It's pretty reliable. It's over 99% reliable. But IP itself, if there's an error, he can't fix it. Do you remember that when at the data link layer, the Ethernet frame had a frame check sequence at the end, and if the Ethernet receiving workstation had the proper MAC address to receive, he was the destination address in the Ethernet frame. He would recalculate the CRC, and if it didn't match, he would drop the frame. So he didn't retransmit it himself. He would depend on an upper layer protocol to do that, TCP. So IP is kind of like that. IP doesn't have any positive acknowledgement and retransmission features. He depends entirely upon the transport layer to do stuff on that. So IP must rely on other protocols for these functions. He relies upon the transport layer, TCP. And it's media independent. So in the case of this example diagram, we have some copper, we have some fiber optic cable, we have some Wi-Fi type wireless. Now, one new term here is maximum transmission unit. When we talked about Ethernet recently, we talked about the fact that an Ethernet frame can encapsulate upper layer data, and like an IP network packet, and that packet has to be at least 64 bytes, but it can be no more than 1,500 bytes in length. So the maximum transmission unit size for an Ethernet frame is 1,500 characters. But there are other layer 2 protocols besides Ethernet. For example, the old IBM token ring, he could handle over 4,000 characters in one token ring frame. So this maximum transmission unit size is set by whatever physical Ethernet or whatever dial-up screeching cats modems, whatever you're using to establish the size. So IP itself, layer 3, he does have the ability to fragment a packet into smaller pieces. Now, IP version 6 doesn't do this, just IP version 4. This causes extra latency or delays because he has to figure out to take these 4,000 characters of data and split it into 3 IP packets. Example of this would be if I had in the 90s, the servers were on a token ring network and the clients, the employees were on a Ethernet-based network. When the data came back from the server, it would have to be fragmented into smaller pieces that would fit on Ethernet, on the Ethernet segment of the circuit. So that caused latency, that caused delay. Now looking at IP version 4, that's our legacy or our network layer protocol type that's been around just forever and ever and ever. So with the purpose of the IP header, the purpose of the header is it has source and destination addressing. So this makes sure that the routers can look at the destination network portion of the address and figure out the best path to get it one step by step to its destination. It contains information for network layer processing, like for example, it counts the total number of hops, and some routing protocols, for example, the old routing protocol RIP, you only got 15 hops, and then you were dropped, and you assume that you were stuck in a circle. So this is used by all devices that handle the packet, typically layer 3 routers. This is the header. So it's in binary. So at the top it says byte 1. That's 8 bits, 8 bits, 8 binary bits, 8 binary bits there. It's 32 binary bits. So the main ones we're interested in is the source and destination fields. The destination IP address is going to be examined by network devices. That they need to determine the best path to forward it to the next hop. And the source address is going to be the address that the destination machine uses to respond to this request. Servers fulfill requests for services and clients request them. So the client's the source IP address, the server's the destination IP address. So the server now knows the IP address of the client machine to send the answer back to this database sort or whatever function he asked for. Okay, version is IP version 4. IP version 4 has a different code. We're going to talk in a later course about differentiated services. This is a quality of service. If I want to put certain types of traffic to the head of the line so they're processed more quickly because they're very sensitive to latency, like a voice over IP telephone call or streaming audio or streaming video, we can use this field for this. There's a header checksum, which is similar to the frame check sequence on the end of an Ethernet frame to make sure that no information in the header, like the IP addresses, got scrambled up. Now I mentioned the hop count, the time to live. This is so that we can prevent packets in a network that's lost connectivity from packets from being routed, going around stuck in a loop and just consuming resources. The protocol field tells us what is this upper layer information that's in this IP packet. It could be a TCP or UDP segment. It could be an ICMP, like a echo request, echo reply, ping traffic. And then we have our 32-bit source address and our 32-bit destination address. Now let's look at IP version 6. The big problems with IP version 4 was pretty much about the mid-90s. We kind of ran out of addresses. We had to come up with some, the Internet Engineering Task Force wizards stayed up late one night and came up with some methods for working around these problems, like network address translation and private inside IP addresses, to make these addresses last longer. Network address translation, there was no direct connection between public addressing. So, well, kind of in the vein of a little story, when I was working in the 90s at the college textbook publisher, we all had public IP addresses on all our machines. There was no network address translation. We hadn't run out of addresses yet. So you could directly ping any workstation machine. We were 167.208.209. something. We had a /16 address. So network address translation sort of solves this problem of running out of IP addresses. It works great with email and web traffic. It causes some problems with things, other things. And when IP version 6 was developed, they eliminated the need for NAT. And since it has 128 bits instead of 32 bits, there's infinitely more number of addresses. So IP version 6 is going to make sure it's going to take all these problems that IP version 4 had. Then what happened to IP version 5? It went from 4 to 6. There was a test version. It used up number 5, and the version we actually put in production was IP version 6. So big improvements is 128 bits instead of 32 bits. So that sounds like it's 4 times bigger. It's actually like 1 trillion times bigger. The header doesn't have as many fields in it. It's easier to process. And there's no need to use network address translation because we have like 1 trillion, more than trillions and trillions and trillions of available addresses. So it's simplified. So it has a source address and destination address. And some of the IP version 4 stuff was removed to improve the performance. So there's a version 6. There's a quality of service. There's a flow label for devices to choose the best path. There's a payload length that tells us how big is the data portion of this. And then the next header is, what is this upper layer protocol that's being encapsulated, just like an IP version 4, TCP, UDP, ping. There's a hop limit, which replaces the time to live, exact same function in IP version 4, and then our source and destination addresses. So it's just very similar to IP version 4, it just has more bits. Extension headers are optional, and they can give extra network layer information. IP version 4 had the ability to fragment, but IP version 6 does not fragment. So they use extension headers to work around this problem of different maximum transmission unit sizes, physical sizes. Now let's look at how a host machine routes, or how a host device routes. Now every host machine has its own routing table. If you fire up your Windows computer and type route print at the prompt, it'll tell you the routing table it has. It has a 127.0.0.1 address. That's IP version 4. It has an address for local hosts and remote hosts. So this is like the decision. When I pick up the phone in the lab and I call the lab manager and say the projector bulb is burned out and you must come in here and replace it. That's a local call in our PBX system. I don't have to dial 9 to get an outside line. But if I want to dial an outside line and call the weather report or something like that, I have to dial 9 first and then dial that number. So similarly, every time a local host machine, say PC1 wants to send to PC2, PC1 needs to determine, is PC2 on my own local network? I can just send it right home to the switch. I can directly put my ping request in an Ethernet frame and send it to the switch. It'll go straight to PC2. That's like me dialing a lab manager. That's a local call. I didn't have to dial 9 to get an outside line. That's a local host. The destination is on the same LAN. We're on the same network. We all have the same network prefix. If it's a remote host, I can tell because the network prefix of the destination will not be my network prefix. And I'll know, oh, I have to dial 9 to get an outside line. Or if you're at home, you got to dial 1214 to call someone and dial us and tell the telephone company it's a long distance call, not a local call. So the source machine has to determine whether the destination is on its own network, like PC1 and PC2, they're both on the same network. They can talk directly with each other. But the remote host machine, he's on another network. The only way I can get to that is through my router. R1 router here, the .1 address on the router, which I call the friendly neighborhood router. He's the only one that has a connection to that other network. I have to take my data and send it to my router, and he in turn will re-encapsulate it in another packet and get it sent to that remote host. So the router is an intermediary device that makes route forwarding decisions. Typically a router, or I hate this terminology, layer 3 switch. Everybody knows that layer 3 device, the network layer, is a router, and a layer 2 device, a data link layer device, is a switch or a bridge. But the marketing guys went crazy and they said, oh, you know, we used to call switches bridges, and they said, oh, bridges, can't call them bridges, that sounds slow, we gotta call them switches. Routers used to be called gateways, that's why they're called default gateways. But when the electronic terminology, electronic technology got better, they put some routing features in the transistors and integrated circuits on switches. So I like our layer 2 Cisco 2960 switches. They can do some layer 3 static routing. They can even be a DHCP server. So the default gateway is, you can use a router, you can use a sophisticated layer 3 switch to be a default gateway for all those employee or student machines that are on that particular individual network. All the devices on an individual network have to have the IP address in the same range. They all have to have the same prefix. For example, at home, you're probably 192.168.1 dot, whatever your 4th octet unique value is. So the default gateway accepts data from that LAN, like your home network, and he forwards it off the LAN to your internet service provider. So if a device has no default gateway specified or it's incorrect, the symptoms are he'll be able to, the PC1 and PC2 will be able to ping each other on the local network, but they won't be able to send and receive traffic from a server that's off the network at another remote branch office or somewhere on the internet. Now, how does the host know its default gateway? You either statically configure it. So in our labs, we've clicked the button that says use this IP address, and we put in the IP address and subnet mask and default gateway. But in most of production environments, we don't have the users do static configuration because that's very burdensome for us IT guys to have to do this. So in the mid-90s, they came up with this dynamic host configuration, which is a server that automatically sends out IP addresses to all the workstations that need them. Pretty much everything in the company except maybe some servers and printers. In IP version 6, there's another scheme for finding their IP address called router solicitation, or we can configure those manually as well. So default gateway is a route in the routing table so that when PC1 and PC2 want to talk to the remote networks, router R1 will have in its routing table a way to get to those other networks. Okay, so I got ahead of myself here. You can type route print or netstat-r, and you'll see the routing table on your individual PC. And you'll see, in this case, we're seeing the IP version 4 routing table in this print on the right side of the print. Got the 127.0.0.1, his own loopback address. And then he's got his network address, 192.168.10.10. And he knows what his default gateway router in is. It's 10.1. Now, let's look at this routing function. A router receives something that a host machine sends out. So in the number 1 print here, the packet has arrived at the router and the destination IP address is 10.1.1.10. Looks like the source address of the machine is 192.168.10.10. So router R1 is going to look at all the bits coming along the source machine, PC1, creates the data. He sends out the bits on the wire. The bits flow through the switch. They go to the router. The router puts those bits together and says, this looks like a valid Ethernet frame. I'll open up the frame and unencapsulate the network packet and look at the packet. It looks like it's addressed to me. And it'll process that data. So router will look at the router R1 looks at that destination IP address, this 10.1.1.10 that's in the header of the IP packet, and he looks in his routing table, and here's his routing table, and oh, he has an entry that matches that. I know about the existence of this network 10.1.1.0. It says router R1, and he says, in order to get information to that, all I got to do is send it out my Ethernet port on the right here, this port right here, and it'll get one step further to that destination, and he'll be able to receive it. Router 2 will repeat this process, and he'll go through the process of forwarding it so that PC2 can receive this data. So the routers all work in conjunction with each other to step by step, hop by hop, send this data to the network. Now, looking at the routing table in a Cisco router, there's 3 types of entries. A directly connected route is one that's on that router. Looking at router R1, he has 2 directly connected interfaces. He has the G00 and the G001. And by virtue of the fact that you configure the IP addresses on those and did the no shutdown command, they're going to appear in the routing table, automatically added by the router. You don't have to do any static routing at all. Now, how does the router know about the remote routes like this route here? He doesn't know about this route. It's not directly connected to him. It's a hop away on another router. So we could either put a static route in the router to tell him about it, or more preferably, use a dynamic routing protocol, which we'll have in our capstone course in the fall. We use Ospf now in the Cisco Networking Academy curriculum. Ospf is a dynamic routing protocol that learns about, I call it routing by rumor. The router R1 and R2 gossip with each other and tell them about all the routes they know about, and then each router has a complete roadmap of the entire network, and he can intelligently forward traffic. Now, looking at these 2 routers at the company we have here, at the internet connection for the ISP, there's a big honking router. It's $1 million router, like a Cisco 7500. It has the 750,000 routes that are in the backbone of the internet. Our little routers, our $1,000 routers we have at our company, don't have the horsepower to handle that. So we're going to set up a default route inside our company. Inside our company, our router is going to have all the dozen routes we have, and then a pointer to the internet service provider. This is called the default route. And it says if you find any IP address, the destination address, and it's not within our internal corporate network, it must be a real world public internet address. Send it to the ISP, and it'll route to there. Static routes have to be configured manually. If there's any change in the topology, the administrator must go in and change all the IP route commands. If it's a small network that doesn't change much, it's okay. If you want a good, if you want high security or control over your network, you can use that. The disadvantage is if you have to change anything, you have to. If you have 2 or 3 routers, it's no big job to reconfigure. But what if we had 300 routers? That'd be a big problem. So normally today we use static routing in conjunction with a dynamic routing protocol to configure that default static route back to our internet service provider. So we don't have to manually configure a static route at each and every device on every router. So dynamic routing is much more wonderful because all I have to do is turn on the dynamic routing protocol on these routers R1 and R2, and they'll automatically find all the other dynamic routing protocols I'm running on the other routers, in the case of what we'll have, Ospf, and they'll build up a routing table of what's the best path to get to everywhere, and they'll stay up to date. If there's a topology change because in this graphic down here, this link has gone down, maybe it was a telephone company or cable company link and it failed, but there's a backup path. You can go this way. So a dynamic routing protocol will find this new best path when the topology is changed, and then everyone will still be able to communicate with the outside world or with the company. Now let's look at this command for looking at the routing table. It's show IP route, and this shows us, it's got a little legend code at the top that tells you like O stands for OSPF, etc. And on this router, we have got some directly connected routes. The C's and L's, C is directly connected. L is like the link local actual IP address of that exit interface that you can route packets to. Then we have an O telling us, oh, this router has learned about an OSPF route from another router. R1 learned it from R2. And then we have our default static route so that the people on our inside of our company network here can all communicate with the internet out here, because our routing tables on our little routers are too small to have those 750,000 routes. We only want a couple dozen routes. We don't want to buy $1 million routers when a little $1,000 router would work just fine. And hang loose a second, and I'll bring up the next slide set. Now, we've had a little thing about ARP in here before. What was ARP? Address Resolution Protocol. We know it as the thing that causes the first ping to fail. Whenever you do a lab, you type ping something and it should work, and ARP waits about 10 or 15 seconds, and then you finally get something and you say, oh my goodness, I thought it had failed there. But it's there for a reason, very good reason. So we need some sort of physical correlation. Here's the big picture. We need some sort of physical correlation between the layer 2 physical MAC address that's conveying our layer 3 packet from one point to another. We need to match up that layer 2 MAC address with the layer 3 MAC address of those devices. Now, when a PC sends out information, let's say PC wants to send out this packet of information. Destination IP address is that laptop computer PC2 over on the right. He knows his IP address. He knows his own MAC address. He knows the destination IP address because she typed in the command ping 192.168.10.11. But what he doesn't know right now probably is that MAC address 555555 on a second PC. In order to send that ping request to PC2, he's got to encapsulate that ping echo Internet Control Message Protocol echo request into an Ethernet frame. And in order to create that Ethernet frame, he knows he has to have the destination MAC address, because the very first part of an Ethernet frame is the destination MAC address. So he has to send out an ARP request. If he hasn't communicated with the other PC2 recently in the last 3 minutes, he will have to send out that ARP request, broadcast request, and learn and relearn that 55555 MAC address so he can completely create that Ethernet frame. So he's only got 3 of the 4 things right now. He needs to learn that 4th thing, which is the destination's MAC address. That's the purpose of ARP. Now, what about if I'm trying to send something to not a PC2 on my network, but another device on another network? In this case, PC2 is on a whole other network, say back at the home office or something. So far as I'm concerned, my MAC address is AAAAAA, and I don't care about, MAC addresses are locally significant only. They're only important only on that individual network segment they're on. I don't care about PC2's MAC address. I only care about what is the MAC address of my default gateway router who can relay it to that other network for me, because I have no direct connection to that second network. I only have the direct connection to the devices in my little part of the company. So in that case, I'm going to determine I have to dial 9 to get an outside line. It's another network. So PC1 is going to say, well, I have to go to that default gateway on R1. I'll just do an ARP request for his MAC address, and I'll relay that to him. And then once a router has received that Ethernet frame, it has MAC address on its destination, he'll process it. Then they'll look in this routing table and they'll pump it out. this 2-hop link between R1 and R2 to get to that destination network. Now, IP version 6, ARP and IP version 4, we call that a broadcast. In IP version 6, it's the same sort of a function, but they decided not to call them broadcasts anymore. Now they call them anycasts. But it does the same sort of a thing. It's sent to all the other devices so that the one device who I know his IP address, I need to learn what his MAC address is. Same problem. I know my address. I know my layer 3 address. I know my layer 2 MAC address. I know the destination machine's layer 3 IP address, but I don't know the MAC address. I've got to learn it. So ARP is the function that correlates or resolves this IP version 4 address that I know of a destination machine to what his MAC address is. I don't know that. And then I'm going to maintain that mapping within my PC for about 3 minutes. It's a temporary mapping because you could, if it's a laptop, you could pick up your laptop and run to another building, and if you held on to it for an hour, you'd have all the wrong kind of address mappings. It wouldn't work anymore. So if you type that command ARP-A, and then you wait 5 minutes, and you type it again, you'll see it's gone. So if a workstation like the first host machine PCA wants to send a frame, he's going to look in his Arp table for the destination IP address and the corresponding MAC address. So if it's in the Arp cache, he'll go ahead and use it. But if it's not in the Arp cache, he needs to find it. So he's going to send out the broadcast on his own local network, essentially saying, calling all stations, you destination device who has the IP address 192.168.1.2. I need to know your MAC address because I need to send you something to you. Sorry about shouting loudly and bothering everybody else, but if you're 192.168.1.2, will you send me back a reply with your MAC address so that I can create this Ethernet frame and send it to you, and you can process the data. So if it's on the same network, he'll find the MAC address of the other device, like PCA and PCB are on the same network. If it's on another network, like back at the home office on the internet somewhere, he'll use his default gateway's MAC address for that. And he'll determine that by looking at the destination network address and saying, if it's on my network, it's the same network I'm on, he must be a local device or plugged in the same switch. I can talk directly to him. I can send out Ethernet, he can hear it. If it's not a different address, it's, oh, I got a dial 9 for an outside line, got to send it to my default gateway router, and I need to learn his MAC address of my default gateway's address, that 192.168.1.1 typically is addressed on people's home networks. So if there's no entry in the ARP table, he's going to send out this ARP request in the form of a broadcast. Now, how do entries get removed from the ARP table? Usually about 3 minutes. Sometimes on routers and switches, they hold on to it for a little bit longer. You can also go and remove them yourself. So you could remove an ARP table from you could clear your ARP cache table on your desktop PC by typing a certain command. You can do that on routers and switches as well. But you don't have to do this automatically after 3 minutes. They'll fade away all by themselves. So if I type on a PC, ARP-A, that shows me all the devices I've communicated with recently and what their MAC addresses are. And now if I need to communicate again with one of these, I don't have to look it up again. I don't have to send out a broadcast. If I want to send to some address that's not in this cache table, I would have to do an ARP request to learn it. On the router or switch, you type show IP ARP, and that shows you the relationship between the IP address and the MAC address. Now, since ARPs are sent in the form of a broadcast, that means every device on the network hears it and processes it. So devices on the network that have a certain IP address, of course, when they receive something that corresponds to their IP address and their MAC address, they'll respond to that. But a broadcast is a kind of a call, a frantic call for help. And it's kind of saying, I'm sending something out and I need help and I don't know the exact MAC address or whatever, and you need to help me. So I need to blast it to everybody. So it's sent, and when switches receive broadcasts, they're compelled to flood these broadcasts out every single port, not just, normally a switch would build a virtual connection between host A and host B, and nobody else would hear this stuff. Now the problem is, can we find the bad guy in this? Oh, there he is, he's the black hat guy. This looks spy versus spy or something. So a bad guy could, for example, use ARP poisoning and pretend to be the default gateway, and everything passes through him, and he can copy your passwords and get your bank accounts and stuff. Now, copper cabling. Copper cabling. Oh, this is IP version 6. The IP version 6 equivalent of ARP is something called neighbor discovery. There's router solicitation and router authorization messages, so you can find and determine your own default gateway. And then there's neighbor discovery if PCA wants to ping PCB, for example. PCA needs to learn PCB's MAC address. So this is the exact same functional equivalent of IP version 4's ARP, except so that you can feel better about it. We're not going to call it a broadcast anymore. We're going to call it an anycast. We still need to line up the layer 2 physical MAC address of that destination workstation with this IP address. I know my own IP address. I know my own MAC address. I know the destination workstation's IP version 6 address, but I don't know its MAC address. So we're going to do the same thing. We're going to send out some neighbor solicitation messages. Hey, if calling all workstations, if your IP address is 2001 DB8 ACAD 111, I need your MAC address because I need to send you a ping or I need to send you some data. So everybody hears it, but the only workstation that responds is PC2, who actually has that unique individual address, and he sends back his MAC address to PC1. Now PC1 can send it. So IP version 6 devices do not use ARP, they use neighbor detection, neighbor discovery. Okay, let's see. I've got to stop this and go to this, and oh, I guess I have to do this. Now, this last chapter is talking about iOS router configuration, and it's really, really similar. This should be deja vu because it's almost like configuring a switch. So let's take a look at this. So we're going to look at settings on IS router, configuring interfaces on the router, and then configuring devices to point to the router is the so-called default gateway, because they used to call them gateways. So they should call them default routers, but they call them default gateway because that's what they've always called them back in the days before they were called routers. So does this look kind of familiar? We're going to attach to the device with maybe a rollover Ethernet, a rollover console cable, and we're going to type host name, maybe R1. If it's a switch, it would be S1. The default host name of a switch is switch. The default host name of a router is router. But we have two routers and we don't want to get confused. So right away, the first thing I want to do is make them R1 and R2. And then I can use Cisco Discovery Protocol and make sure they're all plugged together properly. That's what my favorite trick is when starting a lab. The password is exactly the same, enable secret class. The line console is exactly the same. Line console 0, password Cisco, login. And then line VTY 04, password Cisco, login. And we also have a command that can restrict incoming. VTY stands for virtual terminal. We use that for telnet or secure shell, and we can use that command line transport input to either restrict it to secure shell or just telnet or allow mode. If we don't put that in there, the default is transport input none, and we won't be able to telnet into it at all. That occurred in the last iOS revision. Then we're going to encrypt the passwords like the line VTY and the line console password, so you just can't see them, you just show it on the screen. And then we're going to put a nastygram on the screen that our lawyers told us to say, morning Will Robinson, authorized users only, all traffic is tracked, leave immediately if you do not agree, whatever our lawyers said. So on this router, we've given it the host name, we've done the enable secret class, we've done the passwords for the login, remote login, and console login. We've done the banner messages of the day. And then we type copy run start. You can type copy running -config startup config like he has here, but you can shorten it to copy space run space start. And that'll save your running configuration, which is in RAM, and can evaporate instantly if the power is lost, to the NVRAM chip, which is a chip that doesn't lose its contents when the power is turned on and off. So that way, when the router is turned off and on again, you save the configuration. The router boot process will boot the iOS and look for the presence of a startup configuration file in the NVRAM, and it'll find it and it'll go ahead and run it for you. And you won't have to type it in all over again just because the thing rebooted. Now let's see how we configure our interfaces. So I'm in the router configuration mode, global configuration mode, I'm going to say interface. In our machines we actually have in the lab, it's G0/0 and G0/1. In Packet Tracer, the newer router 4000, like the 4321 router, they have an extra slash, so it's G0/0/0 or G0/0/1. Once I type that interface number, the prompt changes to config-if, and I can put in the description keyword, which is optional. Nothing, no code is executed. It's just a way of adding a comment to refresh my memory about something. Then I can put in an IP, which is an IP version 4 address, or I can put in an IP version 6 address. And then when I'm ready to start using that interface, I'm going to physically turn it on with the no shutdown command, which reverse shutdown means disable, no shutdown means enable. So let's configure G0/0 on R1, this port right here. And it looks like it's supposed to be 192.168.1.10, and it's supposed to be 2001 DB8 ACAD 10::1. So he's in the global configuration mode, interface gig 0/0/0. He has a description, which is not executed at all, just so he can remember what it goes to. Oh, that's my LAN link. Then the IP version 4 address is given, and the IP version 6 address is given, and no shutdown will start it up. And you get right away, you get the Cisco annoyances here. You get the lines that pop up saying state gone up, up, down, up, up, up. Usually right in the middle of, it takes about 10 seconds, and it'll start doing it right when you're typing your next line. That's why I call it the Cisco annoyance. So just press the enter key a couple times to get a clean prompt, and you can start your commanding it. Now let's configure the G0/0/1 port in the same sort of a way. So he's in this case, it's the public network 209.165. He configures that address. He puts the IP version 6 address and performs the no shutdown command to start it up. Now I want to verify I want to do some show commands and check my configuration to make sure it worked properly. So to see the IP version 4 addresses, I'm going to type show IP interface brief. And that'll show me the IP address, but not the subnet mask of my two interfaces. I know they're up and up. If they were administratively down, oh, that's a port that I haven't configured yet. It's not going to operate until I turn them up with a shutdown. To see the IP version 6 stuff, it's most of the show commands, show IP commands in iOS that have been around for 25 years. If you want the IP version 6, you say show IPv6 instead of show IP. IP by itself means IP version 4. And here I can see the IP version 6 addresses of the same exact device. We configured both the IPv4 and IPv6 addresses on it. So I can type show IPv6 interface brief or show IP interface brief. I can show up IP route or show IPv6 route to see the routing table. I can type show interfaces, but that only shows me IPv4. I can type show IP interfaces, again, only IPv4. Or I can type show IPv6 interfaces. And for some reason, they decided not to show us my favorite command, show protocols, or show prot, PRT for short. I like that command because it very quickly shows you, it only works with IP version 4. It shows you all the IP version 4 addresses and the slash number, so you can check did I put in the correct subnet mask? Oh, it's a /24. Good, I put it in properly. The problem with show IP interface brief is it only shows you the network prefix. The network address, it doesn't show you the subnet mask. So if you made a mistake in that command doesn't show it to you. So he's typed show IP interface brief, and he sees all the IPv4 stuff. He types IP6 interface brief, and we can see the status of all those. Now let's look at the routing table. Show IP route is our IP version 4 table. We see the IP version 4 addresses. Show IPv6 route shows us the IPv6 addresses for the same network that we previously configured. Show interfaces, I can type show interfaces and I'll see all of them. But in this case, he typed show interfaces gig 000, and I get really more information than I wanted to know about that entire interface. But if I was troubleshooting some hardware problems, like, oh, look, there's I don't have any errors in here. It looks like it stays pretty good. I don't have any bad Ethernet frames. They're all the right size. So sometimes we use show interfaces to check for a wiring issue, like a corroded connection, or half duplex full duplex issue, or something like that. Show IP interface G00. That only shows us the IPv4 stuff. He shows us the address. In this case, he does show us the subnet mask. Show IP interface brief doesn't show you that. And then a bunch of extra information that's probably not very useful to you right now. Show IPv6 interface, we see the IPv6 addressing information, and he's joined his local group so he can do the router solicitation and neighbor discovery type functions. And there's extra information here about Internet Control Message Protocol. Now, the default gateway is something that needs to be known. In this case, we got 4 PCs, PC 1, 2, 3, and 4, and R1, and we're just showing the left side of the router. The right side of the router there's nothing there, but it goes off to some other network or to an internet service provider. So all of the devices on this network must have the same network prefix. In this case, it's 192.168.10.0 for PC1 and PC2, and 192.168.11. something for PC3 and PC4, because the 2 upper PCs are attached to the upper Ethernet port and the 2 lower PCs are attached to the lower Ethernet port. So the router is capable of forwarding data from PC1 and PC2 if it needs to go to PC3 and PC4, and vice versa. So PC1 and PC2 have their default gateway of 10.1, and PC3 and PC4 have their default gateway of 11.1. And thus they have connectivity with all 4 PCs between the devices shown in this topology. A switch, the warning, Will Robinson. A default gateway on a switch. You must have a default gateway on the switch because the switch is not the router. And so we use the command IP default gateway so that if you're trying to telnet a secure shell into a switch from another network, you're not on that same directly connected network. Just like a host PC needs to have that default gateway command in order to get off his local network and get to all other networks, the remote networks. Switches do too. So we use the IP default gateway command on the switch so that he has the knowledge and information to be able to relay anything something that's not on his IP prefix to his default gateway router, and he will relay that on for him. Okay, I think I've covered everything. Now hang loose. I'm going to stop the recording function.